Okay, so the two papers today, one from Statoil, from Sandra Rodiño Palacios, and also the second one's from Lemstad. So the first paper today is qualification of the duct resonant arrays. This is a recent technology with the extension to pipe arrays. Okay, Sandra?
Yeah, thanks for the presentation. Yeah, I'm still a bit with a cold, so I try to be like, speak up, and so just let me know if you don't hear back there, and I'll keep my bottle of water close to me. So sorry for that. Yeah, so today I'm gonna talk about this device that developed to reduce noise emissions from compressors that would leak into the pipe pin. And I'm specifically going to talk about the so-called pipe array device, and I'm going to guide you through the qualification project that we went through internally in Statoil, and our findings and what do they mean. But first, I want to start explaining why do we need to reduce noise? What is such a big deal? Well, maybe many of you in the audience have been hearing about noise lately, pretty much, and that it's a big issue. And noise is first a health issue. We have all heard about hearing damage. Excessive noise causes hearing impairment, permanent, irreversible, and also tinnitus. But our workers don't only work there, they also live there in their offshore installations. So it also has an impact on the quality of the rest they get. And so that also has an impact on how they perform the tasks afterwards. So it becomes also a safety hazard. It has a detriment on the quality of the man-to-man communication, but also on the radio communication. The kind of commands that they get through the radio might be misunderstood, and then the tasks are performed poorly. But also any warnings that are sent through the PA system, emergency warnings, might be difficult to hear or understand correctly. So, where are we with noise at the moment? So, as I said, it's a high focus in Statoil, but also, as you see in this meeting today, in the authorities and the industry in general. We have set the priority on attacking this problem by using technical barriers. If we can stop the noise at the source, that's the best option, so we don't have to do it along the way. And we know that compressors are a major contributor to noise in our installations. So of course it makes sense to target those machinery that we know contribute the most. So hence that's why I'm here talking about this particular device. And in another level, we also have some kind of responsibility to provide our projects with solutions that they can use, that they're good enough, efficient enough, how they need to use them, where they have to put them in terms of maintenance and life cycle and space usage and so on. Yeah, this I'm gonna give you a bit like the background history of this device in Statoil. Actually, it would start before 2000, when Dresseran as a vendor for the machinery to project was challenged and say, okay, we need you to actually give us a solution to reduce noise further. and a research project was set, and it was funded partially with Statoil. And a few years later, Desran developed what's now called Duct Resonator Array, and it's this device we're talking about today, produced to reduce noise from centrifugal compressors. In 2002, this device was qualified inside Statoil and has been implemented in many installations ever since. As I said, that for use inside compressors, so this device can be applied inside the compressors in the diffuser area, and that's what we first qualified. But after 2007, we learned that actually this device can also be implemented outside the compressor, what we call pipe array, but it's the same device. It's just to differentiate the two different applications. So we call it pipe array because it's installed as a pipe piece to the compressor. And we saw certain advantages. We don't have to actually modify internally the compressor. So if we're doing some modifications, we don't have to stop actually the machinery and put it away and do something to it and be back. And there's no limitations on, okay, does this device actually fit the size of our compressor, or can it run with it? So we saw some advantages that actually our projects could benefit from. So we went ahead and start a qualification process that I'm gonna talk about today. Essentially doing some laboratory acoustic measurements to test the actual attenuation of the device. And the result was that this technology is currently qualified within Statoil, and it's been recommended for use extensively in some of projects, and will be implemented in the future. Now, what is this pipe array? Well, it's essentially a one-piece steel tube that it's perforated, and behind these perforations we have these kind of volumes or acoustic chambers. And this tube, it's lined here in this spool piece, on the walls of this spool piece, and then this piece is applied to the inlet or discharge pipes. The size of this spool piece is actually basically the length is in relation to the diameter of the pipe, and typically is delivered in a size of 4 times the diameter length. How it works, I try to say this simply and fast. So it's based on Helmholtz resonance theory. Helmholtz was a German physicist from the 19th century. So basically, what happens is, what happens is there's a pressure difference between this and this side of these perforations, resulting in some displacement of the air in this small neck. and that produces energy losses by friction and viscosity. And the thing is that those losses are produced at a certain frequency, which basically depends on the different dimensions of these volumes and these openings, etc. So the frequency response of this phenomena is that at a certain frequency we see this peak, so we see this sound attenuation. So all this energy loss is happening. So at that particular frequency. So when we put this pipe array inside our system, what happens is, instead of having a very reflective walls of this pipe, we put this system, and it happens. It goes from reflected to actually absorptive at that frequency that we have tuned our device to. So you can ask me questions afterward if this wasn't clear. So the actual, an example of actual pipe array frequency response we can see here. So what is happening here is that this with the high peak is an example of a common response of a compressor. So they would make a noise that has a lot of energy concentrated in a certain frequency, rather narrow band. So what we do is, okay, we know that in this case was 2500, so we have that kind of compressor. So what we do is we design this, or Dresden actually designs this device so that, you know, the dimensions of these holes and these perforations and these volumes match this frequency. So as you see, this would be the response once we have the pipe array working. So all this energy here, it's been absorbed. And how much is that absorption? Well, manufacturer guarantees at 10 dB overall attenuation, and that with this standard dimension, which is like 90% of some power reduction. So if the machine makes so much power, you take actually 90% of that power away. Yeah, I'm gonna explain now or guide you through this qualification process. So this is internal requirement in Statoil when we have a new technology. And what is the purpose? Well, basically it's to evaluate what risk we have, what consequences this device might have in our operations. In this case, it was mainly to verify the acoustic attenuation of this device, if it's as what the manufacturer was announcing, and because we had the opportunity to do these measurements, and I'm going to explain further how we made them. We decided that, okay, let's investigate further. How can we actually place this? What happens if we have larger or smaller pipe array? If we place it that way, try to work a bit with it and see if we can give our projects a more flexible solution that just like you have to put this big piece of pipe in your system. Sorry. So we went to our Dresden's workshop and we measure what we call sound insertion loss. So basically we had a loudspeaker that was sending a broadband signal. That means that we were exciting many frequency bands at once. And we placed one microphone in the piping, then the array system, and another microphone at the end of this whole system. So basically what we measure is what the difference between these two signals. So what happens before and after this pipe array. So theoretically here we would have the noise. When we look at this signal, that noise should have been reduced. So by comparison, we know how much and how well and where this attenuation has happened. In our case, we had the chance to test two. These are 4 times the diameter length pipe arrays. So we had the possibility to, as I said, play a bit with the configurations, which I explain further on. So if we look at just verifying, okay, is this device actually attenuating as much as the vendor is saying? So in the band, in our case, our arrays were tuned to attenuate a compressor that would have a tonal, tonal noise characteristic at 2500, like you saw before, this kind of peak at 2500. So in the frequency of interest would be 2 to 3 kilohertz. We measure actually 14 to 18 dB attenuation for this 4D length type of array. Overall attenuation, if we sum in all the different octave bands, it would be 7 to 8. It's a bit lower than what they are promising, but it's more of a result of the mathematical summation than anything, because it's a very narrow band. So let's say that at least we measure 8 dBs in our laboratory conditions. So here you can say this is the signal that we would have in the first microphone at the beginning. So this is our broadband noise signal, and then this is what happens after, when we measure after the pipe array. Now, as I said, we had these two pipes that we could play with, and we decided to check, okay, what would happen if we have different lengths? If we would place them with a bend, if we would separate, instead of having one for the system, could we have two different ones? And the investigation of this is, we know that it's challenging to find place in layouts to fit these kind of systems. So we try to see how flexible and this system could be, or if there would be other ways to place it, or would it be more convenient to have it longer or shorter, etc. The results from this, all this playing, so we can see that, so of course if we don't have any array, we simply have no attenuation. We can see this is almost linear. Actually, there's a big jump, so to speak, if we have a 6 diameter length system. And if we would have two systems, this is pretty interesting, because actually if we would have two systems, what we wanted to try is what would happen if we have one duct resonator array inside the compressor, and we would also have one as a pipe array outside the compressor. And we would get like 2 times 10 as they promise, right? Each system gives 10 dB. So of course not, but there's a RAM promise plus 3 dB when we put a second system, and we actually measured that it was you have 60% more attenuation if you add the second system. So if we say 10 dB, that would roughly be 6 dB more. So it's actually much more than what they expected. And here you can see like how sort of the system works. Basically, what we were doing is just covering parts of the array or uncovering them. So this would be the total. This line would be the total 8 diameter length. If we cover this part, then we get to that point, and so forth. So we're just basically narrowing the frequency, in which frequency bands this actually act in, and therefore how much attenuation is given us. As you saw, also we tried to place them with a bend, and instead of like in series. And actually, you don't even see, but here there is two signals. One if they were placed one after the other, and another one if they were placed with the bend, and it's basically the same. So there was no detriment in the performance if we place them after a bend. So that was a good thing to see. still in all, the pipe array should always be placed closest to the source. This device works best the closer to the source that it's placed. Yeah, so that is not everything about acoustics. I'm gonna briefly talk about mechanics. We also assess mechanical and process conditions in this qualification. So basically, we review what if the materials that this array is made of are okay, if it's impeding in any way the process, there's any pressure drop, and so forth. And we couldn't really find so many downsides. Even some concerns about there would be some liquid accumulation, perhaps that would get like stuck in this perforation and so on. We found solutions for if we place them horizontally when it's the problem that can get accumulated. Actually, we could just not perforate the bottom part, and we would not have any. That would not have any impact on the sound attenuation, and we could solve this worried about liquid accumulation. It could also be install some drain capability. So mainly the downsides are not concerned with maintenance, or because there's nothing to be maintained. There's no material that can get loose or worn out. And we've seen before that after a few years, you go back and open and see how it looks like and still in perfect shape. So it has more to do perhaps with things like cost and weight than maintenance or corrosion or any of these considerations. So I think I went a bit fast, but in conclusion, well, what we saw is that this device actually give us a very good, efficient, significant attenuation to control actually noise emissions from compressors to propagate through our piping systems, so we can in a way spare all this extra piping insulation that we have to put along the way. We saw that actually it is not such a rigid system, that there's some potential flexibility there for implementation, and that's good. To encourages our projects to look this device with all their eyes and try to implement it in our very challenging layouts. At the beginning we said that we have put a high priority in using technical barriers and stop the noise at the source as a efficient way to deal with noise in our projects, and certainly this device give us that, puts it closer to comply and meet our goals. And certainly this, I would like to highlight that this is a positive collaboration between a vendor and a client. If you have challenged each other, you can get to very good efficient results. And last point, of course, way forward, it's what we're looking for is actually to recommend and install this device in many other projects. First for compressor noise, certainly, but we have identified, or we are in a way to identify all the uses or applications and machinery with similar noise characteristics. This that has to be a tonal, very narrow frequency band noise. So it could be used perhaps in turbo expanders or HPO systems, but of course this needs to be further identified, so maybe that would be our way forward. That would be it. Thank you.
My perspective is broader than Sandra's. I'm pretty much here trying to summarize my own experience looking into these systems. As you probably understand already, Mike has also been doing quite some investigation into this, and he's read through my paper and he didn't find too much wrong in it, so hopefully it'll be okay. So, do we really understand gas compressor pipe noise? That's the question. I go through with you here, give you a system overview, and why do we have this noise problem? I'll show you some results from measurements of bare pipes. This is the most of the reason for this presentation is in this. Look into the prediction method. Is it time to change it? And finally, proposal for a design strategy for new projects. If you'd asked the guy at the right there, some 8 years ago, do you really understand gas compressor noise? I think the answer would be no. You called out here, we have this noise problem in module M something. Can you come and have a look at it and come propose for something to do? Well, we have the compressor. It's a nice little thing compared to the rest of what's out there. And it's something we're used to handle. But then we have all of this. And from our perspective, what's all this for? There's a hell of a lot of pipes in there. What's it actually doing? What's it doing in the process-wise, and what's it doing for noise? Obviously, you go to the control room and you get this overview, which helps a lot, of course. But really not before you simplify it a little bit. And you end up with something like that. And now we start to understand what's going on here. Now the gas flows here through the system. This is the noise source, much like a fan in a ventilation system. We have additional items here, the scrubber, which takes away moist and heavy components before the gas is getting into the compressor. If you don't do this, you can be in big shit trouble here. That has happened, and compressor failures are quite expensive. On the other side, you get higher pressure gas, but the process of compression has increased the temperature. That's not wanted, so we have to cool it down before it goes further on. And there are several other items in this, but this is the main process. Translating it to noise, it looks a bit like this. Again, the noise source in here, but the propagation of the noise is in both directions. The scrubber acts as a sound silencer somehow, unintended. It's a big device, heavy. We don't quite know how much that is, depends on several things. But it doesn't really emit sound. It's pretty dead. Here, however, it's also doing a job as a silencer, but it's also itself quite a source of noise. So it might look like this. These pictures are not from the same installation. The scrubber like a big tank here. The compressor. And an after-cooler system. Move on to show you some results of noise from a case where all insulation of the gas piping was removed due to corrosion issues. And this is something you must reckon that you have to do after some 10-15 years of operation. So it's not unusual. What we saw as a consequence, one feared that there will be a lot of noise, a lot more noise in the areas. But actually, it turned out to be fairly moderate. So the question from the client was, okay, how much insulation do we really need to reapply here? Maybe we can get on with not applying everything. This picture is from somewhere else, again, but it shows what can happen. And needless to say, this can be really, really dangerous. It can blow your whole installations a piece. So what we really need, of course, is something like this. I don't think it exists. The noise increases that we observed was, as I said, fairly moderate. It's not easy to compare one-to-one before and after, it turns out, because things are changing. In this area, though, we saw a pretty marked change, but we think that's due to something else, that is local effects. Only a few local areas affected by this. So in general, just a couple of decibels increase. And this area and this area are the critical ones. So you can see the other ones are lower. So our scope then, translated to acoustics, determine the sound intensity, rank order each line contribution, and finally provide recommendations for new pipe insulation. And to be more specific, we go and measure surface vibrations, then estimate the sound intensity, and finally calculate the total sound power to the area. Now, these are a bit technical terms for you, I guess, but we needed to do it by vibrations. We couldn't measure this directly. It was too much sound coming from everywhere. Vibrations and sound, that's not quite the same thing. I mean, things can vibrate, but it's not really correlated 100% to vibration, to the sound. So this shows we use a very simple relationship for this so-called radiation factor, which is the connection between vibrations and sound. And I just want to point out that a large pipe is better at producing sound for a certain vibration than a smaller pipe, much like a big loudspeaker and a small loudspeaker. The sound from these systems, Sandra talked a little bit about this, what really happens here. Here you can see a very narrow band spectrum. Again, this is a different installation. And we see the rotational speed of the impeller is here at about 150 Hertz. It's the main rotation. But this is usually not a problem in terms of noise. You can see that and you can hear it, but, well, you can hardly hear it actually because what's happening here. And this is the blade pass frequency, which is actually this frequency multiplied by the number of blades. So typically here you end up somewhere in from 1500 to 3,000-4,000. This is the first stage system at 2.2 kilohertz. And how does it sound? It's actually extremely annoying. I spent several days in such areas and it's not a nice thing to do. Results. There were two systems here, a low pressure system with 3 stages and a similar high pressure system. Pipe diameters. You have bigger pipes in the first stages and the pressure increases and you get more condensed gas and you have smaller piping. And the sound, this is a sound power level per meter. But just look at the relative numbers here. You go on here, you can see it decreases quite significantly by the stages. High pressure system, not quite the same tendency, but it's still there. It decreases as you go down, but not as consistently. There is more spaghetti than this. This is the main piping. Here we can see some auxiliary piping, and they have varying noise emission. This is like blind piping to the PSV, the pressure shutdown values. You have recirculation lines where you want to reduce your capacity. It can be very, very noisy. And cooler medium pipes also. In particular, this cooling medium, when we go out there to see what happens, it's always a problem. Not always, but very, very often a problem with these, say, seawater valves are very noisy. And we have often end up recommending insulating piping or replace this valve. It seems always this is a noisy valve. Again, a picture from somewhere else than this side. So these are the main results from this case study, which is it's not often that you get a chance to measure on uninsulated piping. So again, look at the relative numbers. Without any, the total pipe length here was about 600 meters. And without any insulation, we have 122 is the number. Now by calculation, we could take the worst 100 meters, the pipes emitting the most noise, and it gives us 5 decibel less. 200 meters down by 9 decibel. And the third alternative, half of the piping re-insulated, would give us 16 decibel. 16 decibel in percent, Halvor, how much is that? It's a lot, he says. Yes, it's 97%. So, well, couldn't resist playing with this exercise here. This is an old system, well, 15, 20 years old, I don't quite know. I can't be more specific, I shall not reveal anything more about that. But it was not an option at the time of design. But if you assume 10 decibel reduction of the silencers and apply them to the most noisy stages, what will happen? I mean, like this. Like a ventilation system, it's very parallel to that. You apply a silencer on both sides of the fan, or the impeller in this case. And you have this third alternative. Just 10% of the insulation would do the same job as 1/3 of the insulation. So a significant improvement. And with very, very little insulation applied. Main conclusions. It would seem that half of the original pipe insulation was actually a waste. Much of it to smaller pipes. We see clearly the highest noise emission from the first stages. We recommend to reapply something like 30 to 50% of the insulation. In this case, maybe the lower number would do, due to other noise sources in the area. And finally, a silencer like a PDRA may significantly reduce insulation need on this smaller system. This is not a very big system. So that was that case study. It showed us that maybe we are doing something a little bit wrong here, applying too much insulation. And it's easy to understand why when you have been through an exercise to try to predict noise emission yourself, because that's not so simple. To predict noise out of these pipes, we need a noise inside, we need a transmission loss of the piping, and then we get a noise outside. This transmission loss is due to many things. Coincidence, I don't even think I will say that, it's too difficult. Another one. So we have boundary layer turbulence, propagating plane waves, flow separation and increased turbulence at discontinuities, and finally mechanical excitation. So now I'm going to go through all of this with you and show you the formulas. No. It turns out that in good engineering practice, there's just one effect that's really important. But still not easy. This authority here, Norton, says there are no explicit mathematical relationships for the parametric dependence on coincidence. Predicted results are qualitative and have to be obtained from an experimental databank. Well, doesn't sound too promising. But we can measure and see what's going on. So, as usual, frequency on the x-axis, decibel here. So the higher, the better here. So at low frequencies, the reduction is very high, 60 decibel and more than that. That's because the pipe is not really good. It may move, but it doesn't really, you don't get the sound out. To be very simple. But then we have a dip here, and then a steady rise up here again. This frequency here is pretty easy to calculate. It's a ring frequency. So it has to do with the diameter and one wavelength on the outer side of the pipe. This one is not so easy to calculate, but we can usually estimate it reasonably well. But this region here is where things happen. It's usually a problem area. And in this area we have this awful tone. So, transmission loss here at coincidence depends on pipe diameter, thickness of the pipe, sound velocity in the pipe material, steel usually, sound velocity in gas, and internal pressure inside. So we are kind of getting there now. But again, if you turn to the literature, you'll see different ways to handle even the physical parameters, like the thickness and the diameter. So I calculated myself through a 4-stage system using these two different methods here. If you look, the consequences in decibels is that with the method 1, if you double your thickness, you get 6 decibel improvement. Twice as thick pipe. I mean that's getting heavy, but let's say we do that. And the same thing, if you halve the diameter, you get 6 decibel improvement. And this is improvement here in this attenuation. So it goes up with a smaller piping and a thicker piping. But in here you only get half of the effect.
But is this practical, double the thickness and half diameter? when you see the piping layout.
Yes.
If you want to increase the thickness to double, you need the flexibility also in the piping system. So if you increase the thickness, you lose.
Yeah, I'm not saying that you can do this always. It's just that these are the relationship, and it's a natural. When you go to smaller piping, you get a higher thickness usually because you need that, because of the higher pressure. So it's a natural thing that comes out of the design that we don't do for noise, but it's done for process reasons, right? So this is a 4-stage compressor system where I actually calculated all this through all the stages. And we can see that the pipe thickness goes up. This is not due to noise, this is a process design. Yeah, due to pressure. And the pipe diameter goes down. Easy understandable. Not the details, but the concept. So these are the results using these two different methods for this system. The blue line shows transmission loss is about the same for all stages. There's very little change here. Whereas the second method, you get much higher attenuation for these higher stages, third and fourth stage. It's a significant difference. And here it's actually 12 decibels. Now just look, I'm lying a little bit to you. 35 is the 0 point here. So it's not dramatic, but it's significant difference. So, method 1 seems to be more in line with empirical data, our measurements. And Mike confirms this. He's also seen that. Method 2 seems to give conservative values for higher stages. So if this is correct, there might be potential for less acoustical insulation on the smaller and thicker piping. Methods. Method 1 is Norton. Method 2, this one, is the recommended method in NORSOC S002. So this is the one method we should use. And it is conservative. Now we looked at noise emissions, airborne noise, just emitting from the pipe. This is showing something else that we see sometimes can be a problem, particularly in large systems. You see the mounting of this, in the case of the cooler, is there is no elasticity here. It's bolted solidly to the beam, to the structure here. And the result is that this structure here emits a lot of sound, actually more than the cooler itself in this case. This can be avoided by using thin pads of elastic material. This avoids structure-borne noise at these high frequencies. And there are systems available to do this for piping. No problem. One also sees sometimes very soft, low frequency anti-vibration mounts like this. And this was actually retrofitted after some time because one feared too much fatigue and too much stress in the piping system. So what shall we do based on these experiences? Well, one thing we certainly should do is to look at NORSOC when we design a new system. Design goal for area 85 decibel, and really if it's tonal sound it should be even 5 decibel less. This is not simple. Generally, installation of low noise equipment shall be the primary noise control measure, and this also applies to piping systems and valves and things. Low noise. Do we do this? Do we use low noise equipment when we can? Well, it seems we have some way to go. To summarize the methods, the first method is a silencer that Sandra has talked about. It's much like a sound silencer in a ventilation system. Elastic supports, pipe insulation, and finally low noise valves for the cooling system. The silencer takes away 10 decibels as a rule of thumb, and we can maybe cash in another 5 decibel for the pure tone reduction. It's a durable device, it's a long life. Elastic supports, we can say it's needed for large systems, but maybe not for smaller ones. Thin sheets is sufficient to take out the noise. And it's not costly if you apply it the first time. If you want to do it afterwards, if you mount everything, it is very costly. Now this also has a long life in general. Pipe insulation is the most effective, but it works only locally. But you can have up to 25-30 decibel reduction. Corrosion issues, as I talked about, you need to remove and reapply this in the course of a lifetime of an installation, 1, 2, maybe even 3 times. All take away and inspect, and you have a constant worry about what's going on under there. Unless you use titanium piping, perhaps. High lifetime costs, but it comes year after year. Finally, low noise valves. This reduces insulation needs, but some of these designs may be more prone to clogging because they use smaller, rather than one big opening, there are several smaller ones, usually. So, recommendations, and all of this perhaps has a question mark attached to it. Apply silencers on all compressor stages, or at least consider to do that. It removes the tonal character almost completely. Use vibration isolation of main pipes and the aftercoolers, or everything. And this is the most difficult one. Evaluate, make a model of your area using various pipe insulation scenarios and using more accurate methods than we have today. Apply insulation where you obviously need it, and set aside space to insulate later. And Mike tells me that this is actually a problem because if the space is available, it's very easily taken up, so you don't have this option afterwards. Very, very important to ensure you have this option afterwards. Then you have to say what insulation class you have to use. Low noise valves, or you just take the punishment of insulating more piping. And this may be, in order to get good designs through, look at the lifetime costs. Things that are more expensive now may be cheaper in the long run. And I'm just near the end now. Insulation classes here. It may be this noise is quite high frequency, so these class 6 designs may be okay in many cases and for some of these lines. So it saves weight and some money. Well, there is more work to do to understand this. I mean, this is me working, but this is the end for now. And thanks to my colleague Telman Eichler for doing a lot of measurements, and to Mike Newman here. Thank you.